The room is dark, not the dark of a moonless night, which is still full of starlight and scattered photons and the faint glow of the atmosphere itself. This is a different kind of dark, the dark of a closed room at 3 in the morning, when the only light is the dim standby glow on a piece of electronics, and the only sound is the slow movement of air through a vent. In this room, in this dark, something is moving through you. It is not a metaphor, it is not a spiritual idea, it is a physical substance, a stream of particles, billions of them every second, passing through your body without resistance. They do not interact with your skin or your bones or the neurons in your brain. They move through the walls, through the floor, through the earth itself, as though none of it were there. And they have been doing this for your entire life, every second of every night, while you slept and while you woke, and while you sat in the dark wondering if there was anything in the room with you. There is. About 85% of the matter in the universe is this invisible substance. We can map where it gathers around galaxies. We can weigh it inside clusters of galaxies 1,000 times the mass of the Milky Way. We can watch it bend the path of light from distant stars. We can read its fingerprint in the oldest light ever detected, a glow that was released when the universe was a newborn, and we have no idea what it is. Hello, and welcome to Penumbra. This is a story about dark matter, about the invisible majority of the cosmos that saturates the room you are in right now and passes through you without asking anything and without leaving a trace. If you would like to support the channel, you can subscribe and like this video, and in the comments, tell me where you are listening from and what time it is. I read them. Here is the question this video will hold. What is this invisible thing that built the scaffolding of the universe, that holds galaxies together, that moves through your body at this moment, and why, after nearly a century of knowing it is there, do we still not know what it is made of? By the end, you will understand exactly how we came to know it exists, the evidence that makes it undeniable, and the deep, honest inventory of what remains unknown. The story begins not with a dramatic discovery, but with a quiet Dutch astronomer counting stars in the 1930s and noticing that the numbers did not add up. The man was Jan Oort, and the year was 1932. Oort was one of the great astronomers of the 20th century, a figure of immense patience and precision, the kind of scientist who could spend a decade on a single measurement if the measurement was worth making. He had already made his name a few years earlier by demonstrating that the Milky Way rotates as a whole, using the motions of stars to prove that our galaxy is a spinning disk with a center far from the Sun, a result that itself had overturned an older picture in which the Sun sat near the middle of everything. Oort would go on, later in his career, to propose the existence of a vast shell of icy bodies at the edge of the solar system, a reservoir of comets so distant that it now carries his name, the Oort cloud. But in 1932, that discovery was still decades away. He was looking at something closer to home, the bobbing up and down of stars above and below the plane of the galactic disk. The stars in the Milky Way do not sit perfectly flat in a single plane. They oscillate slightly as they orbit the galactic center, moving up through the disk and then down again, pulled back each time by the gravity of all the mass concentrated in the midplane, much the way a ball dropped through a hole in a trampoline would rise, fall, rise again, always drawn back toward the center of the sheet. The speed of that oscillation tells you how much mass is doing the pulling. A strong gravitational pull means the stars snap back quickly, completing their vertical cycle in a short time. A weak pull means they drift slowly upward before turning around, taking longer to complete the same cycle. Oort measured this directly. He took a sample of nearby stars, catalogued their positions and velocities perpendicular to the galactic plane, and used the physics of that oscillation to calculate how much mass had to be sitting in the disk around the Sun to produce the motion he saw. The answer was uncomfortable. He needed roughly twice as much mass as could be accounted for by the visible stars. There were not enough stars, not enough glowing or even faintly shining material to explain the force that was keeping the stellar disk pinned together. He called it the missing mass, a term that would echo through astronomy for the rest of the century, though not always attached to what Oort had actually found. Oort was careful about what he claimed. He did not announce a new form of matter. He noted the discrepancy, floated a modest explanation. Perhaps there were faint stars or cool interstellar gas that current instruments simply could not detect, and moved on to other work. The missing factor of 2 was, in his telling, a puzzle to be resolved by better observations, not a crisis in the foundations of physics. The missing mass might be nothing more than dim stars, burned out cinders too cool to register on a photographic plate, scattered through the disk like unseen sand between the visible grains. Oort was not, in fact, the first to notice that the numbers did not quite add up. A decade earlier, in 1922, the Dutch astronomer Jacobus Kapteyn had attempted a cruder version of the same calculation, using stellar motions to estimate the total mass density in the solar neighborhood, and had flagged a similar tension between the mass implied by stellar dynamics and the mass visible in the form of stars. Kapteyn's instruments and methods were far less precise than what Oort would bring to the problem 10 years later, and his result drew little attention at the time, treated as a rough estimate awaiting better data rather than a genuine puzzle. It is worth holding on to this detail because it shows the discrepancy was never a single astronomer's isolated finding. It had already been glimpsed once, set aside once, and needed to be glimpsed again, more carefully, before anyone took it seriously enough to keep pulling at the thread. But the factor of 2 did not close. It widened. As astronomers turned their instruments from the immediate solar neighborhood to larger and larger scales beyond the local stars, beyond the Milky Way entirely, the missing mass grew from a local curiosity into something vast and structural. To understand why this eventually became so unsettling, it helps to be precise about what astronomers mean by ordinary matter. Ordinary matter is everything built from protons, neutrons, and electrons. It is the matter of stars and planets and interstellar gas and the cells in your own body. It is the matter described by the periodic table, the matter that interacts with light, that can be heated and cooled and formed into chemical bonds. When astronomers speak of the visible universe, they do not mean only the objects bright enough for an optical telescope. They mean all the ordinary matter in every form it takes, the scorching gas inside galaxy clusters that glows only in X-rays, the cold molecular hydrogen hiding inside dark nebulae, the dead white dwarfs and neutron stars that have burned through their nuclear fuel and gone quiet. Even counting every last scrap of it, the stuff that shines and the stuff that hides equally, the total falls far short of the gravity holding the universe together. The first confirmation of this came not from counting stars at all, but from the physics of the universe's first few minutes. The theoretical foundation for that physics was laid in 1948 in a paper by Ralph Alpher and George Gamow that also carried, somewhat as a joke, the name of the physicist Hans Bethe, added purely so the author list would read Alpha, Bethe, and Gamow, a pun on the first 3 letters of the Greek alphabet. Despite its playful origin, the paper was serious physics, working out for the first time how light elements could have been forged directly from the hot, dense conditions of the early universe, rather than only inside stars. In the extraordinary heat immediately after the Big Bang, when the cosmos was still hot enough to fuse protons into heavier nuclei, the entire universe briefly operated like a single, vast nuclear reactor, exactly as that paper described. The exact abundances of the light elements forged in that furnace: hydrogen, helium, deuterium, a rarer form of helium called helium-3, and a trace of lithium depend exquisitely on how dense the ordinary matter was at that moment. If there had been more baryons, more protons and neutrons packed into that early plasma, the fusion reactions would have run faster and hotter, producing more helium and burning through the deuterium almost completely. If there had been fewer baryons, deuterium would have survived in much greater abundance, since there would have been less material available to burn it away in secondary reactions. Astronomers can measure these primordial abundances today by looking at gas clouds so pristine they have never passed through a star, pockets of hydrogen illuminated from behind by the light of distant quasars, whose faint absorption lines record the chemical fingerprint of the early universe almost unchanged since it was a few minutes old. The observed ratios of these light elements, measured across dozens of such clouds and cross-checked against the oldest stars in the galaxy, pin the baryon density of the universe to a narrow, well-defined range. There has always been one thread in this picture that refuses to sit quietly. Lithium. The abundance of primordial lithium predicted by Big Bang nucleosynthesis, given the baryon density fixed by deuterium and helium, is roughly 3 times higher than the abundance actually measured in the oldest, most metal-poor stars in the galaxy. This is called the lithium problem, and decades after it was first noticed, it remains unresolved. It may be an issue with how lithium is destroyed or diluted inside old stars over billions of years. It may point to some subtle piece of nuclear physics from the first 3 minutes that has not yet been correctly modeled. It is a small crack in an otherwise remarkably successful picture, and it is worth naming honestly rather than smoothing over, because it is exactly the kind of loose thread that reminds you the story of the early universe. However solid it looks, is not yet complete in every detail. What Big Bang nucleosynthesis tells us, lithium problem aside, is that ordinary matter, every proton, neutron, and electron that exists can account for, at most, about 5% of the total energy density of the universe. 5%. That number, derived from nuclear physics and the spectra of gas clouds billions of light years away, has been independently cross-checked by an entirely different measurement. The cosmic microwave background, the afterglow of the Big Bang itself, which we will return to later in this story. The two measurements, arrived at by completely different routes, agree. The universe contains about 5% ordinary matter. The rest is something else. And the rest is not a small remainder. The total matter in the universe, ordinary plus dark, makes up about 31% of the total energy budget. Dark energy, a separate and even stranger phenomenon that is driving the accelerating expansion of space itself, accounts for most of the remaining 69%. But that is a different story for a different night. Within the realm of matter alone, dark matter outweighs ordinary matter by more than 5 to 1. For every kilogram of protons and electrons in the universe, there are 5 kilograms of something that is not made of protons and electrons. Something that does not interact with light. Something that has never been touched, captured, or identified in any laboratory on Earth. The 5% exception, the luminous, ordinary, familiar world, is all we have ever directly seen. Every star in every galaxy, every planet, every mountain and ocean and living cell, every supernova and black hole and neutron star, every grain of dust drifting silently between the stars, all of it, the entire visible inventory of the cosmos, is a thin frosting on a cake made of something we cannot see. Jan Oort's missing factor of 2 was the first quiet tremor of this realization. It did not announce itself as a revolution. It was a data point that did not quite fit, filed away by a careful man who assumed it would eventually resolve. But the discrepancy did not resolve. It grew. When astronomers turned their telescopes from the solar neighborhood outward, toward the great clusters of galaxies scattered across the sky, the missing mass stopped being a factor of 2 and became a factor of hundreds. The man who first saw that, and who first gave the invisible substance its name, was not a careful Dutch astronomer counting stars near home. He was a combative Swiss genius working at the edge of respectability, and the numbers he found were so extreme that almost no one believed him for 40 years. The Coma Cluster of galaxies lies about 320 million light-years from Earth, in the constellation Coma Berenices. It is not a small collection. The cluster contains well over 1,000 identified galaxies, a swarm of stars so dense that the entire system is held together by its own mutual gravity, orbiting a shared center of mass, the way stars orbit inside a single galaxy. On a deep photographic plate taken through a large telescope, the cluster looks like a cloud of luminous dust. Hundreds of tiny elliptical smudges packed into a patch of sky no wider than the full moon. In the early 1930s, the astronomer Milton Humason, working at Mount Wilson Observatory in California, was measuring the radial velocities of these galaxies, how fast each one was moving toward or away from Earth, by spreading their faint light into spectra and searching for the telltale shift of spectral lines caused by the Doppler effect. Humason's own path to the telescope was unusual. He had started at Mount Wilson as a mule driver, hauling construction supplies up the mountain during the observatory's early building years, then worked as a janitor on the site, and eventually rose, through sheer persistence and a remarkable eye for observational work, to become one of the finest observers of his generation, working for years alongside Edwin Hubble during the period when Hubble was establishing that the universe is expanding. Humason's spectra of the Coma Cluster were difficult and demanding work. The galaxies were faint, and the photographic plates of the era required exposure times stretched across multiple nights just to gather enough light. What his measurements revealed was not simply the expansion velocity of the cluster as a whole. The individual galaxies within it were moving relative to one another at speeds that seemed far too high, some approaching, some receding, the full spread of velocities, what astronomers call the velocity dispersion, working out to roughly 1,000 kilometers per second. That is an enormous speed for objects supposedly bound together by gravity. It meant the galaxies were careening around inside the cluster like agitated insects in a jar, moving far faster than the gravity of the visible stars alone could possibly contain. This is where Fritz Zwicky enters the story. Zwicky was a Swiss physicist working at the California Institute of Technology, a man of ferocious intellectual confidence and almost no patience for social diplomacy. He referred to some of his Caltech colleagues as spherical bastards because, he explained with characteristic bluntness, they were bastards any way you looked at them. He fought constantly with his peers, was frequently dismissed as difficult or unreliable, and was, for much of his career, simply not listened to. And yet Zwicky was also the kind of scientist who proposed ideas that seemed wild in his own time and were later proven correct, again and again, often decades after he first suggested them. Working with the astronomer Walter Bade, he helped establish the modern classification of supernova into distinct types based on their spectra, and the two of them coined the very term supernova to describe the extreme brightening of a dying star. He also correctly proposed, years before it could be confirmed, that supernova explosions produce neutron stars, an idea that sounded almost like science fiction at the time and turned out to be exactly right. His partnership with Bade did not end amicably. The two men eventually stopped speaking to each other entirely, reportedly after a dispute during the Second World War, in which Zwicky, a Swiss national, questioned Bade's loyalties as a German citizen working in the United States, a rupture that lingered for years and that neither man ever fully repaired, even as they continued, separately, to shape the field. When Zwicky looked at Humason's velocity measurements for the Coma Cluster, he reached for a tool from classical physics called the virial theorem. The virial theorem is a relationship connecting the kinetic energy of a system, the energy of motion of its individual parts, to its total gravitational potential energy. In a stable, gravitationally bound system like a cluster of galaxies, the average kinetic energy of the galaxies in motion must be balanced by the gravitational pull generated by the total mass of the system. If the galaxies are moving very fast, the gravitational pull holding them together must be correspondingly strong, and a strong gravitational pull requires a great deal of mass. Zwicky took Humason's velocity dispersion of roughly 1,000 kilometers per second and used it to calculate the total mass required to hold the Coma Cluster together against that motion. He then compared that number to the mass he could estimate from the combined starlight of every visible galaxy in the cluster. The cluster required roughly 400 times more mass than the starlight indicated. 400 times. Not twice as much, not a factor of a few, but a number so large it implied that almost the entire mass of the cluster existed in some form that emitted no light whatsoever. Zwicky published the result in 1933 in the Swiss journal Helvetica Physica Acta. In that paper, he gave the invisible substance a name in German, Dunkel Materie, dark matter. The paper did not cause a revolution. It caused, at most, a shrug. The missing mass problem in galaxy clusters was noted by a handful of specialists and then largely set aside. Most astronomers assumed the missing mass was not a new kind of substance at all, simply hot gas, ordinary matter that had not yet been detected because the necessary instruments did not exist. Gas at millions of degrees emits its light almost entirely in X-rays, and X-ray astronomy, which requires instruments carried above the atmosphere, was still decades away. It was reasonable, at the time, to suppose the Coma Cluster was full of ordinary intracluster gas, too hot to register on any optical plate, and that this gas quietly accounted for the missing mass. Later, more careful measurements would reduce Zwicky's original factor of 400 substantially, correcting for errors in his estimate of the cluster's distance and total luminosity. But even after correction, the discrepancy remained enormous, on the order of many tens of times the visible mass. The hot gas explanation is worth following to its conclusion, because it shows how a reasonable idea can be right about something and still fail to solve the problem it was invoked for. When X-ray astronomy finally arrived in the 1960s and 70s, carried above the atmosphere first on rockets and then on dedicated satellites, astronomers pointed the new instruments at galaxy clusters and found that the intracluster gas was, in fact, real exactly the hot, X-ray emitting gas that the skeptics of Zwicky's day had predicted must be there. In a cluster like Coma, this gas turned out to contain considerably more mass than all the stars in all the cluster's galaxies combined. The visible galaxies, it emerged, are only a minority of the ordinary matter in a cluster, with most of the rest in the form of this diffuse, superheated gas glowing only in X-rays. For a moment, it might have seemed the missing mass had been found. But when the mass of the gas was carefully measured and added to the mass of the stars, the total ordinary matter still fell far short by roughly a factor of 5 or 6 of the mass needed to hold the cluster together at the velocities Humason had measured. The gas was real. It was even the dominant form of ordinary matter in the cluster, and it still was not remotely enough. The skeptics had been right that hot gas existed and had gone undetected, and wrong that it would resolve the discrepancy. The missing mass survived the discovery of exactly the thing that was supposed to explain it away, which, in retrospect, was one of the clearest early signs that dark matter was not going to turn out to be ordinary matter, hiding in some overlooked form. Zwicky was not the only person to notice something was wrong with the Coma Cluster, and it is worth pausing on the astronomer, who came to nearly the same conclusion by a different route, and has been almost entirely forgotten by comparison. In 1936, an American astronomer named Sinclair Smith, working at the Mount Wilson Observatory using much the same kind of velocity data that Humason had gathered, applied the virial theorem to the Virgo cluster, a separate, somewhat closer collection of galaxies. Smith found that the Virgo cluster, too, required far more mass than its visible stars could explain by a factor of roughly 100. His paper appeared in the Astrophysical Journal, in the mainstream of American astronomy, in a far less obscure venue than the Swiss journal where Zwicky had published 3 years earlier. And it, too, was largely ignored. 2 independent astronomers, using 2 different clusters and slightly different data, had converged on the same unsettling conclusion within a few years of each other, and the field simply moved on. It is a small, sobering fact about how science actually proceeds, that a correct and well-supported result does not automatically compel belief, that a community can look directly at strong evidence and choose, not through malice but through habit and assumption, to file it away rather than follow it. There was another reason Zwicky in particular was easy to dismiss, and that reason was Zwicky's own manner. He presented his conclusions with an air of absolute certainty that irritated even those inclined to take his physics seriously. He was not wrong about dark matter, but he was also not the kind of scientist who builds consensus. A genuine shift in scientific understanding requires not just a correct observation, but a community willing to be persuaded. And Zwicky, brilliant as he was, did not cultivate that willingness. He made his claim, coined his term, and the field largely moved on to other problems. The missing mass sat quietly in the literature, cited occasionally, explained away more often for nearly 4 decades. What Zwicky did do, in 1937, 4 years after the Coma Cluster paper, was make a second prediction that would prove crucial to the eventual vindication of everything he had claimed. He realized that if a galaxy contained enough mass, its gravity could bend the path of light passing near it, acting as a gravitational lens, splitting the image of a more distant object into multiple copies, or distorting and magnifying it. Einstein's general theory of relativity had already predicted that gravity bends light, and the dramatic confirmation of that prediction during the solar eclipse of 1919, when a British expedition led by Arthur Eddington measured the deflection of starlight passing near the sun's limb, had made Einstein a household name almost overnight. But Zwicky calculated that a galaxy, carrying the combined mass of 100 billion suns, would act as a far more powerful lens than a single star like the sun ever could. A background galaxy, aligned closely enough behind a foreground one, could have its light bent into multiple images arcs, rings, distorted copies scattered around the foreground mass. And crucially, the degree of that bending would be a direct measurement of the total mass in the lensing galaxy, dark matter included, regardless of whether any of that mass emitted a single photon of its own. Zwicky wrote that gravitational lensing would let astronomers weigh nebulae, his term at the time, for what we would now simply call galaxies, and he believed the effect should be detectable with the telescopes already available. He did not live to see the prediction confirmed. He died in 1974, but the technique he described on paper, decades before anyone had the instruments to carry it out, would eventually become one of the most powerful tools ever built for weighing the invisible. Gravitational lensing was not the only independent method that would eventually confirm what Zwicky and Smith had found. Decades later, once X-ray telescopes finally existed above the atmosphere, astronomers gained an entirely separate way to weigh a galaxy cluster. The hot gas filling the space between cluster galaxies, reaching temperatures of tens of millions of degrees, glows brightly in X-rays, and the way that gas is distributed depends on the total gravitational pull holding it in place. Hot gas, under weaker gravity, spreads out further and cools more, while gas held by a deeper gravitational well stays more tightly confined and hotter. By measuring the temperature and density profile of the X-ray emitting gas, and assuming it sits in a stable balance between gravity pulling inward and gas pressure pushing outward, a method called hydrostatic equilibrium, astronomers can calculate the total mass of a cluster using a technique that has nothing to do with galaxy velocities or the bending of light. Satellites including Rosat and later Chandra and the European XMM Newton Observatory applied exactly this method to dozens of clusters beginning in the 1990s and arrived at total masses in close agreement with both the older virial estimates and the newer lensing maps. 3 separate methods, the speed of galaxies, the bending of background light, and the physics of hot gas held in balance converging on the same missing mass, each blind to the assumptions built into the other 2. The missing mass problem did not vanish in the decades after Zwicky's death. It lay dormant, noted occasionally by specialists, explained away as often as not. What was needed was a measurement that could be made inside individual galaxies rather than entire clusters, repeated for enough galaxies that the pattern, whatever it turned out to be, could no longer be dismissed as a fluke of one unusual system. That measurement required 2 things: a spectrograph sensitive enough to capture faint light from the outer edges of spiral galaxies, where starlight thins to almost nothing, and an astronomer willing to spend years pointing that spectrograph at one galaxy after another, trusting the data even when it refused to behave. The astronomer was Vera Rubin. The spectrograph was built by a man named Kent Ford. Vera Rubin was born in Philadelphia in 1928. She fell in love with astronomy as a child, watching the sky from her bedroom window and building her own simple telescope out of cardboard tubing. She applied to Princeton for graduate study and was turned away before she could even submit an application. Princeton's astronomy department did not accept women into its graduate program at the time, and would not do so for decades to come. Rubin earned her master's degree at Cornell instead, and her doctorate at Georgetown, working under George Gamow, one of the founding theorists of Big Bang cosmology. Her earliest research, on the large-scale streaming motions of galaxy clusters, it was controversial from the start. Some colleagues suspected the pattern she reported was an artifact of the data, rather than a real feature of the universe. It was an early, formative lesson. The universe does not always present its structure cleanly, and neither does a scientific community always welcome an inconvenient result. Even after she had established herself, the barriers did not disappear. Palomar Observatory in California, one of the premier research telescopes in the world at the time, did not permit women to observe there at all until 1965, and Rubin became one of the first women ever granted the chance to use it. In the mid-1960s, Rubin began working with Kent Ford, an instrument builder who had developed a device called the Carnegie Image Tube, an early form of electronic light amplifier that multiplied the effective light-gathering power of a telescope many times over. Before Ford's tube, capturing a usable spectrum from the faint outer disk of a spiral galaxy could require an entire night's exposure on a photographic plate, and even then the result might be too weak to measure precisely. Ford's device changed the calculation. It meant Rubin could point a telescope at the dim, extended edges of a galaxy, the region where the last handful of stars and clouds of gas orbit far from the visible core, and still obtain a spectrum clean enough to measure a velocity with confidence. It was unglamorous, patient, technical work, repeated galaxy after galaxy, night after night, at observatories in Arizona and Chile. The physics behind the observation was simple to state. A spiral galaxy like Andromeda, or our own Milky Way, is a rotating disk. Stars and clouds of gas orbit the galactic center under the pull of gravity, the same way planets orbit the sun. Near the center, where most of the visible mass is concentrated, orbital velocities should be high. Farther out, past the bulk of the stars, the gravitational pull should weaken, and orbital velocities should fall the same pattern that governs the solar system, where Mercury races around the Sun at tremendous speed while distant Neptune drifts along at a fraction of that pace. This decline, named Keplerian after the astronomer who first described planetary motion this way, is the signature of a system where nearly all the mass sits at the center. Rubin expected to see the same signature in spiral galaxies. A rotation curve, a graph of orbital velocity plotted against distance from the center, rising quickly near the core, then falling steadily toward the edge. She did not see that. In Andromeda, and then in galaxy after galaxy that followed, the rotation curve rose and then flattened. It did not fall. Orbital velocities stayed high, sometimes even climbing slightly, all the way out to the farthest point she could measure. Where the visible starlight had faded almost to nothing, the gas clouds were still orbiting at 250 kilometers per second, held on their paths by a gravitational pull that could not possibly be coming from the small amount of visible matter remaining out there. The first results from Andromeda were published in 1970. Over the following years, Rubin and Ford observed spiral after spiral, dozens of them, of every size and luminosity, and every single one showed the same flattened rotation curve. The phenomenon was not a quirk of one unusual galaxy. It was universal. Each spiral appeared to be embedded in a vast, roughly spherical halo of unseen mass extending far beyond its visible disk, a halo containing 5 to 10 times more material than all the stars combined. The stars and glowing gas that photograph so beautifully through a telescope were merely the luminous center of a much larger, invisible structure. As with Oort and Kapteyn, and as with Zwicky and Sinclair Smith, there was an earlier glimpse that no one had followed. Back in 1939, a young astronomer named Horace Babcock had measured the rotation of Andromeda for his own doctoral work and found rotation speeds in the outer regions that were surprisingly high, a hint, in retrospect, of exactly the flat curve Rubin would map decades later with far better instruments. But Babcock's data was limited. The interpretation at the time was uncertain, and the result was generally attributed to other effects, such as light being absorbed by dust or unusual physics in the outer disk, rather than to any missing mass. The hint sat in the literature, as these hints so often did, glimpsed and set aside, waiting for someone with better tools and the patience to take it seriously. It is a pattern that runs through this entire story. The crucial observation is frequently made years before the field is ready to believe it, by someone whose instruments were not quite good enough to force the issue, or whose result was too easily explained away, or who simply lacked the standing to make anyone listen. Rubin's observing runs were rarely comfortable. She spent long nights alone at remote telescopes Kitt Peak in Arizona, Lowell Observatory in Flagstaff, at a time when some of those facilities had no women's restroom, because none had ever been needed before. She solved the problem, by her own later account, by taping a paper skirt over the sign on the men's room door and continuing her work. She was not looking to make a point. She was looking for data, and she trusted what the data told her, even when it contradicted everything she had been taught to expect. In interviews given decades later, she described the slow, almost anticlimactic dawning of the realization she kept expecting the rotation curves to finally turn over and fall the way the textbooks said they should, and they simply never did. There was no single moment of revelation, no flash of insight in a darkened observing room. There was a gradual, patient accumulation of evidence, galaxy after galaxy, until the pattern became impossible to argue with. Rubin herself was cautious with language. She rarely used the term dark matter in her own writing, preferring to speak simply of non-luminous matter, or to present the rotation curves themselves and let the numbers make the case. She thought of herself as an observer, not a theorist, someone reporting what the galaxies were doing, not someone building a grand new picture of the cosmos. But the implication of her results was inescapable, and she knew it. In a landmark review published in 1978, she presented flat rotation curves for 10 separate spiral galaxies, establishing beyond reasonable argument that the missing mass problem existed inside individual galaxies, not merely in the rare and extreme environment of a galaxy cluster. Wherever astronomers looked, it seemed, dark matter was there. At almost exactly the same time, an entirely independent confirmation arrived from a different country and a different technique. Albert Bosma, a graduate student at the University of Groningen in the Netherlands, had been studying spiral galaxies using radio telescopes rather than optical spectrographs, tracking the 21-centimeter emission line produced by clouds of neutral hydrogen gas. The great advantage of that radio signal is that hydrogen gas often extends much farther from a galaxy's center than its visible starlight does, letting Bosma trace rotation curves out to far greater distances than Rubin's optical work alone could reach. His 1978 doctoral thesis presented rotation curves measured well beyond the optical edge of galaxy after galaxy, using a completely different instrument, a completely different part of the electromagnetic spectrum, and a completely different research group on another continent. His curves were flat too, all the way out. The dark halos were not an artifact of Rubin and Ford's particular equipment or method. They showed up in radio data just as clearly as they had in optical spectra, and they persisted to distances where the visible mass of the galaxy had become almost negligible. While the observers gathered data, theorists were approaching the same puzzle from an entirely different angle. In 1973, Jeremiah Ostraker and James Peebles at Princeton published a paper asking a deceptively simple question: are spiral disk galaxies even stable, on their own, without an unseen halo holding them together? Their answer was no. A thin, self-gravitating disk of stars, they showed mathematically, is dynamically unstable left to itself. It develops a bar-shaped distortion that grows until the elegant spiral shape rearranges itself into something else entirely. Yet the sky is full of stable, long-lived spiral galaxies that have clearly kept their shape for billions of years. Oostreicher and Peebles concluded that this could only happen if each disk were embedded in a much more massive, roughly spherical halo of surrounding matter, providing the additional gravity needed to stabilize the whole system. A halo, they calculated, needed to be at least twice the mass of the visible disk, and probably considerably more. Their theoretical argument, published even before Rubin's definitive 1978 review, gave dark matter a second, completely independent form of support. Not just the stars moved too fast, but the galaxies could not hold their shape without it. The convergence of these three independent lines of evidence, Rubin's optical rotation curves, Bosma's radio measurements, and Oostreicher and Peebles' theoretical stability argument, turned dark matter from a speculative curiosity into the standard model of galactic structure within the span of about a decade. Every astronomy student since has learned, as a matter of textbook fact, that a typical spiral galaxy contains 5 to 10 times as much dark matter as visible matter. The beautiful, photogenic disk of stars that appears in every image from a space telescope is only the luminous tip of something vastly larger, an invisible sphere with a scattering of light at its center. Vera Rubin never received a Nobel Prize for this work, despite it being one of the most consequential observational results in 20th century astronomy, and despite decades of advocacy from colleagues who considered the omission indefensible. She continued working and mentoring younger scientists, particularly women entering the field, until her death in December of 2016. Years later, a new observatory built high in the mountains of Chile, designed to photograph the entire visible sky every few nights for a decade, mapping billions of galaxies in unprecedented detail, was named in her honor, the Vera C. Rubin Observatory. It is, in a very literal sense, built to keep doing what she started, pointing an instrument at the sky and trusting whatever the data says, however inconvenient. We will return to it before the night is over. Here is the fact that changes how you think about your own existence. The stars that light the night sky, the sun that rises every morning, the atoms that make up your body, and the planet beneath your feet, all of it exists because dark matter went first. In the early universe, ordinary matter was too hot and too tightly bound to radiation to begin collapsing into structures on its own. The pressure of trapped photons pushed back against any clump of gas trying to form. Dark matter, immune to that pressure because it does not interact with light at all, felt none of that resistance. It began collapsing under its own gravity far earlier, forming the first gravitational wells, dense knots and threads of invisible mass long before ordinary matter was free to follow. Only later, once the universe had cooled enough for electrons and protons to combine into neutral atoms and radiation to stream away unimpeded, did the ordinary gas finally fall into the wells that dark matter had already dug. The scaffolding was waiting. Without it, the tiny density variations present in the early universe simply would not have had time to grow into galaxies within the age of the cosmos as we know it. The Milky Way would never have formed. The sun would never have ignited. The carbon and oxygen inside your own cells would never have been forged inside a stellar furnace. The entire chain of events that produced you depends on a framework of invisible matter that began collapsing under its own gravity while the universe was still young, silent, and dark. That is not metaphor. That is the current, well-tested understanding of cosmology, supported by several independent lines of evidence that we will walk through across this story. You exist because an invisible ocean of dark matter, 5 times more abundant than the ordinary matter you are made of, began to pool and clump within the first few 100 million years after the Big Bang. The visible universe, every star, every galaxy, Every living thing is a secondary phenomenon, a thin layer of light painted onto a dark and much older skeleton. And yet, for all the certainty in this picture, one question remains stubbornly unanswered. What is the dark matter actually made of? The rotation curves tell us it is there. The stability of galactic disks tells us it must be there. Neither one tells us what it is. Answering that question would require an entirely different kind of effort. A search that would eventually send physicists deep underground, into tanks of liquid xenon and crystals of germanium, cooled to within a fraction of a degree of absolute zero, waiting years for a single particle to leave a single trace. The flat rotation curves that Rubin and Bosma measured in the 1970s did more than confirm that individual galaxies sit inside massive dark halos. They opened a much deeper question. If dark matter dominates the gravity of every galaxy today, how did galaxies come to form in the first place? Answering that meant looking back much further than any individual galaxy, back to the first few 100,000 years after the Big Bang, when the universe was a nearly uniform soup of particles and radiation, and the very first seeds of cosmic structure were just beginning to stir. The central problem is one of timing. In the standard picture of cosmology, the universe began impossibly hot and dense, then expanded and cooled. For its first 380,000 years, it remained too hot for electrons to bind to atomic nuclei. The cosmos was a plasma, a churning sea of free electrons, protons, helium nuclei, and photons, all tightly coupled together by electromagnetic forces. In a plasma, photons cannot travel more than a short distance before scattering off a charged particle and changing direction. Light, in effect, was trapped. This tight coupling meant ordinary matter and radiation moved together as a single fluid. Any patch of the universe that happened to be slightly denser than its surroundings would feel an outward push from the trapped photons, resisting compression, even as gravity tried to pull the patch further inward. The result was not collapse, but oscillation waves of compression and rarefaction, rippling through the primordial plasma at more than half the speed of light. The same basic physics that produces sound waves in air, playing out on a cosmic scale. These acoustic oscillations, as they are called, would eventually leave a permanent imprint on the cosmic microwave background, a story for later in this night. But because ordinary matter remained tightly coupled to radiation throughout this era, those oscillating overdensities could not grow into permanent, collapsed structures. The baryons stayed trapped in the oscillating fluid until the universe cooled enough 380,000 years after the Big Bang for electrons and protons to finally combine into neutral hydrogen atoms, an event cosmologists call recombination. Neutral atoms do not scatter photons nearly as effectively as free electrons do, and the moment recombination was complete, the trapped light broke free, streaming outward in every direction to become, eventually, the faint microwave glow we detect today. Only then was ordinary matter released from radiation's grip and finally free to begin falling together under its own gravity. 380,000 years sounds like an immense stretch of time by any human measure. On a cosmological clock, it is barely an instant, and that brevity turns out to matter enormously. The density fluctuations imprinted on the early universe were extraordinarily small. Measurements show variations of only about 1 part in 100,000, a contrast so faint it is almost easier to describe as almost nothing than as any specific number. Gravity is, relatively speaking, a weak force, and it works slowly on such tiny seeds. If ordinary matter alone had been forced to wait until recombination before it could even begin collapsing, there simply would not have been enough time. Not within the roughly 13.8 billion years the universe has existed for those faint seeds to grow into the rich structure of galaxies, clusters, and cosmic filaments we observe today. Left to itself, a universe made only of ordinary matter would still be, even now, an almost featureless haze of gas. No galaxies, no stars, no planets, no one to notice any of it. Dark matter solves the timing problem precisely because it does not interact with light. Because it was never coupled to the radiation fluid in the first place, it felt none of the outward pressure holding ordinary matter's density fluctuations in check. It was free to begin collapsing under its own gravity from the very earliest moments after the Big Bang, tens of thousands of years before recombination, while ordinary matter was still locked in its oscillating dance with trapped photons. The tiny overdensities in the dark matter distribution grew steadily during that head start, pulling themselves together into roughly spherical concentrations that astronomers call halos, the first gravitationally bound structures to exist anywhere in the universe. These halos formed in a hierarchy, smallest first, merging over time into larger and larger structures, building the scaffolding of the cosmos from the bottom up, long before a single star had ignited anywhere. The very first stars to exist, a population astronomers refer to as Population 3, are thought to have ignited inside exactly these small, early dark matter halos, roughly 100 to 200 million years after the Big Bang, made purely of hydrogen and helium, with none of the heavier elements later generations of stars would inherit from earlier stellar deaths. These first stars are thought to have been far more massive than typical stars today, burning briefly and violently before collapsing. No Population 3 star has ever been directly observed. They may be too distant, too short-lived, or too rare, in the exact form theory predicts for any existing telescope to have caught one but their expected fingerprint. A peculiar pattern of light absorption from the surrounding hydrogen gas they would have illuminated is one of the primary targets of the next generation of radio telescopes now under construction. Every one of those first stars, and every star that has formed since, condensed inside a gravitational well that dark matter had already carved out for it. When recombination finally arrived and ordinary matter was released from radiation's grip, it found the gravitational wells already dug and waiting. The dark matter halos were there first, their mass already concentrated, their gravitational pull already strong. Ordinary gas simply fell into the wells that had been carved out ahead of it, heating as it fell, radiating some of that energy away, and gradually settling into the centers of the dark halos, where it eventually condensed into the first stars and the first galaxies. Every luminous structure we can photograph through a telescope, every disk, every spiral arm, every cluster of newborn stars is ordinary matter that fell, belatedly, into scaffolding that dark matter had already been building for hundreds of thousands of years. Cold dark matter was not the only candidate seriously considered for this role, and it is worth telling the story of the alternative that lost, because it shows how the cold part of cold dark matter was established through genuine trial and error rather than assumed from the start. In the 1970s and into the early 1980s, a number of cosmologists, including the influential Soviet physicist Yakov Zeldovich, argued that ordinary neutrinos, genuinely known particles, rather than a hypothetical new species, might themselves supply the missing mass, provided they carried even a small amount of rest mass. Neutrinos of this kind would have been moving at close to the speed of light in the early universe, making them what cosmologists call hot dark matter. The difference between hot and cold dark matter turns out to matter enormously for how structure forms. Fast-moving hot dark matter tends to smooth out small-scale density fluctuations almost as quickly as they appear, since the particles simply stream away from any small clump before gravity has a chance to hold it together. This predicts a universe where enormous structures, vast pancake-like sheets of matter, form first, and smaller galaxies condense only later by fragmenting out of those larger sheets, a scenario cosmologists called top-down structure formation. The observational test came from simulations. In the early 1980s, Sandra Faber, along with Simon White and Carlos Frenk researchers, who would become central figures in the computer simulation of cosmic structure, ran calculations comparing what a universe dominated by hot, fast-moving neutrinos would actually look like against what one dominated by slower, cold dark matter would produce. The hot dark matter scenario struggled badly to reproduce the universe actually observed. Real galaxy surveys showed small galaxies already assembled and orbiting within larger structures at a much earlier cosmic epoch than top-down, pancake-first formation could easily explain. Cold dark matter, by contrast, naturally produces bottom-up structure formation, small halos collapsing first and merging upward into larger ones, matching the observed universe far more closely. By the mid-1980s, the hot dark matter hypothesis had been largely abandoned in favor of cold dark matter, not because anyone had directly detected either kind of particle, but because only one of the two scenarios actually reproduced the universe. Astronomers could see through their telescopes. It is a clean example of a wrong idea being retired honestly once the evidence against it became clear, rather than clung to out of habit. In 2019, James Peebles, one half of the Ostraker-Peebles partnership that had argued, back in 1973, that spiral disks require a stabilizing halo, was awarded the Nobel Prize in Physics for his broader body of theoretical work in physical cosmology, work that laid much of the mathematical foundation for exactly this picture of structure growing out of the early universe's tiny imperfections. It was a long overdue recognition of a decades-long research program, one built not around a single dramatic discovery, but around the patient, cumulative work of getting the physics of the early universe right, piece by piece, until the whole framework held together. This picture is not simply a plausible story stitched together after the fact. It has been tested directly, using computer simulations that follow the evolution of dark matter under gravity from the early universe all the way to the present day. The first of these landmark simulations was published in 1985 by 4 cosmologists: Mark Davis, George Efstathiou, Carlos Frenk, and Simon White, in a paper that became known simply by their initials. They simulated a cubic volume of the universe filled with cold dark matter particles, starting from initial conditions consistent with the tiny density fluctuations already known from other measurements, and then let gravity act, computationally, across billions of years of cosmic time. Even in that first relatively low-resolution attempt, the result was striking. The dark matter organized itself into a network of filaments and knots, a cosmic web that looked remarkably similar to the actual large-scale distribution of galaxies already being mapped by observers. 2 decades later, in 2005, a much larger and more ambitious successor, called the Millennium Simulation, led by Volker Springel and a large international collaboration, followed more than 10 billion particles of dark matter through the entire history of the universe, from shortly after the Big Bang to the present day, inside a simulated cube more than 2 billion light-years on a side. It remains one of the most influential simulations in the history of cosmology, not because it introduced new physics, but because its sheer scale and resolution let researchers trace, in extraordinary detail, exactly how the first small dark matter halos merged, over billions of simulated years, into the galaxies, clusters, and vast cosmic voids we observe today. Modern successors with names like Illustris and Eagle have gone further still, adding not just dark matter, but the full complexity of ordinary gas physics, star formation, supernova explosions, the growth of black holes reproducing the detailed properties of real galaxies with striking fidelity. But underneath all of that added complexity, the skeleton is always the same, a web of dark matter that collapsed first, providing the gravitational infrastructure into which ordinary matter later flowed. Strip dark matter out of any of these simulations, and the universe that results is almost perfectly smooth. No clusters, no filaments, no voids, nothing resembling the sky we actually observe. The cosmic web is not an abstraction confined to a supercomputer. It has been directly observed. Large galaxy surveys, among them the 2-degree Field Galaxy Redshift Survey and the Sloan Digital Sky Survey, have mapped the 3-dimensional positions of millions of real galaxies across enormous volumes of space. Plot those positions, and you do not see a random scatter of points. You see filaments stretching across hundreds of millions of light-years. You see thin, sheet-like walls of galaxies. You see vast, nearly empty voids, regions where galaxies are almost entirely absent, sometimes hundreds of millions of light-years across. One of the largest known, the Boötes void, is roughly 330 million light-years across and contains only a scattering of galaxies where a region that size should hold thousands. An emptiness so complete that an astronomer once remarked that if the Milky Way sat at its centre, we would not have discovered other galaxies existed until well into the 1960s, simply because there would have been almost nothing near enough to see. The distribution of visible galaxies traces, with remarkable fidelity, exactly the kind of web that dark matter simulations predict galaxies, scattered like dew along invisible threads, dense where the dark matter web is dense, sparse where it thins into a void. There is a further, more exact confirmation buried inside that same galaxy map, and it connects this story directly back to the acoustic oscillations described earlier. The sound waves that rippled through the primordial plasma before recombination did not vanish without a trace once the photons streamed free. They left behind a faint but measurable preference in how galaxies are spaced relative to one another, a subtle tendency for galaxy pairs to be separated by one particular distance, slightly more often than by others, a relic scale frozen into the cosmic web. At the moment, light and matter decoupled. Cosmologists call this signature the baryon acoustic oscillation, and it shows up as a small, characteristic bump in the statistics of how galaxies cluster across large volumes of space. The Sloan Digital Sky Survey detected this bump clearly in 2005, measuring galaxy separations across hundreds of thousands of galaxies, and its scale matched almost exactly what the cosmic microwave background predicted for the same frozen sound wave, measured billions of years earlier in an entirely different form of light. It is the same oscillation observed twice, once as a pattern in ancient radiation, and once as a pattern in the modern positions of galaxies, two snapshots of the identical physical process, separated by billions of years of cosmic history, agreeing with each other to remarkable precision. The Milky Way itself sits inside a dark matter halo of enormous proportions. That halo is roughly spherical, with a radius of about 200 kiloparsecs, some 650,000 light-years, more than 6 times the diameter of the visible stellar disk we can actually photograph. The total mass locked up in that halo is roughly 1 trillion times the mass of the Sun, perhaps somewhat more. By comparison, the combined mass of every star in the Milky Way comes to about 60 billion solar masses, a small fraction, once gas and dust are added in, of the halo's total. The luminous Milky Way, the band of stars stretching across a clear night sky, the spiral arms mapped so beautifully by radio telescopes, is a minor component, a sprinkling of light scattered across the surface of a vast dark sphere. That dark halo is not perfectly smooth, and one of the clearest ways we know is a European satellite called Gaia, launched to measure the positions and motions of more than 1 billion stars across the galaxy with extraordinary precision. Among its discoveries are long, thin streams of stars moving together on nearly identical orbits that stand out clearly against the general population of the galactic halo. The shredded remains of smaller dwarf galaxies that fell into the Milky Way long ago and were slowly pulled apart by its gravity, their stars strung out along the orbit of their original, now destroyed home. One such stream, nicknamed the Gaia Sausage, for the elongated shape of its stars' orbits when plotted together, is thought to be the remnant of a smaller galaxy that collided with the Milky Way roughly 8 to 11 billion years ago, an encounter significant enough that it likely puffed up and reshaped part of the Milky Way's own stellar halo in the process. Another, the Sagittarius stream, is the still unfolding wreckage of a dwarf galaxy being torn apart by the Milky Way right now, its stars strung in a great arc that loops entirely over the poles of our galaxy, the visible evidence that the Milky Way is still, in the present day, growing by consuming its smaller neighbours. exactly as the hierarchical, bottom-up picture of structure formation predicts it should. These streams are not simply beautiful debris. Their exact shape and the rate at which they gradually disperse depends sensitively on the distribution of dark matter they are moving through, since any lumpiness in that surrounding halo tugs unevenly on the stream and leaves a detectable signature in how it stretches over time. Reading the fine structure of these streams has become one of the newest tools for testing whether the dark matter halo is as smooth as the simplest simulations suggest, or carries the kind of substructure, smaller surviving clumps, orbiting within the larger halo that the missing satellites problem and the too big to fail problem both hint at. There are puzzles at the small scale, and it is worth naming 3 of them honestly, because they keep this entire picture from sounding tidier than it actually is. The first is the missing satellites problem. Cold dark matter simulations predict that a galaxy like the Milky Way should be orbited by hundreds of smaller dark matter subhalos, dense clumps of surviving material left over from the hierarchical merging process, and each of those subhalos, in principle, ought to host a small dwarf galaxy of its own. In practice, astronomers observe only 50 or 60 dwarf galaxies orbiting the Milky Way, small, faint satellites, with names like Fornax, Draco, and Sculptor, not the hundreds predicted. The second is the cusp core problem. Simulations predict that dark matter density should rise steeply toward the very center of a halo, following a profile that grows sharply as you approach the middle. But observations of small dwarf galaxies often show something flatter, a broad, roughly constant density core, rather than a sharp central spike. The third, sometimes called the too big to fail problem, is subtler still. Simulations predict that the largest, most massive dark matter subhalos orbiting a galaxy like the Milky Way should be dense and massive enough that they could not possibly have failed to form visible stars, and yet several of the actual satellite galaxies we observe appear far fainter than those simulations would predict for objects of their size. None of these 3 problems has toppled the standard picture, and it is worth being precise about why. Each one likely reflects the messy physics of ordinary matter interacting with dark matter at small scales physics that early, dark matter-only simulations simply left out. Energy injected into a small galaxy's gas by exploding supernovae can heat that gas and blow much of it away entirely, preventing star formation in a subhalo that otherwise would have hosted a visible dwarf galaxy, which helps resolve the missing satellites problem. That same explosive feedback, dragging gas outward through a small halo, can also drag dark matter along with it gravitationally, smoothing a sharp central cusp into a flatter core over billions of years, which speaks to the cusp core problem. When these baryonic effects are folded into modern, higher-resolution simulations, all 3 small-scale tensions ease considerably. Though none has been resolved with complete certainty, they remain live, active areas of research, an honest reminder that a framework can be overwhelmingly successful at large scales, while still carrying real, unresolved tension at small ones. Confirmation of the dark matter halo's overall structure has come from a completely different direction in recent years. The Dark Energy Survey, a project that spent several years photographing a large fraction of the southern sky, specifically to measure the subtle, statistical distortion that foreground mass imposes on the shapes of background galaxies. Its resulting maps of dark matter distribution across enormous patches of sky align closely with where galaxies themselves are found clustered, providing yet another independent confirmation, entirely separate from rotation curves or cluster dynamics, that the invisible scaffolding really is where the visible galaxies say it should be. The question that follows naturally from all of this is whether we can see that scaffolding directly, rather than only inferring it from how galaxies move or how simulations behave. Is there a way to map dark matter itself in something closer to real time, using nothing but gravity as a tool? The answer was predicted in 1937 by the same man who first named dark matter. Fritz Zwicky calculated, in a paper barely noticed at the time, that a galaxy massive enough could act as a gravitational lens, bending the light of anything positioned directly behind it. The idea followed straightforwardly from Einstein's general theory of relativity. Mass does not simply attract other mass from a distance. It curves the very geometry of space-time, and light traveling through that curved geometry follows a bent path. The effect had already been confirmed during the solar eclipse of 1919. Zwicky's insight was that a galaxy, carrying the mass of 100 billion suns, would bend light far more dramatically than a single star ever could, enough, in principle, to split a distant background galaxy's light into multiple visible images. It took more than 40 years for the prediction to be confirmed. In 1979, a team of astronomers working at the Kitt Peak National Observatory in Arizona found a pair of quasars sitting unusually close together on the sky, separated by only a few arc-seconds. When they took detailed spectra of both, the two turned out to be identical, the same redshift, the same spectral features, the same brightness, down to fine detail. They were not two separate quasars at all. They were two images of a single, more distant quasar, its light split into a double image by the gravity of an unseen foreground galaxy, sitting almost exactly along the line of sight. It became the first confirmed gravitational lens, and it opened an entirely new window onto the distribution of mass across the universe. Strong lensing of this kind, multiple images, arcs, complete rings of light wrapped around a foreground mass, is dramatic, but it requires an almost perfect alignment between background source, foreground lens, and observer, and such alignments are rare. One of the most striking examples discovered since is what astronomers sometimes call the Einstein cross. A single distant quasar, its light bent by an intervening galaxy into 4 separate images, arranged in a near-perfect cross pattern around the foreground galaxy's core, discovered in the mid-1980s by the astronomer John Huchra and colleagues. It remains one of the most photographed gravitational lenses in the sky, precisely because the geometry is so clean and so visually striking. But most galaxies and clusters are not perfectly aligned with anything behind them, and a subtler version of the same effect operates everywhere, all the time, whether or not a dramatic multiple image ever forms. Every foreground mass, every galaxy, every cluster, every unseen filament of dark matter imposes a small, statistical distortion on the shapes of the countless background galaxies behind it, stretching them very slightly and aligning them tangentially around the foreground mass. This effect, called weak gravitational lensing, is far too subtle to notice in any single background galaxy, whose own natural shape swamps the tiny distortion. But measure the shapes of thousands or tens of thousands of background galaxies across a patch of sky, and average out their intrinsic randomness, and the coherent distortion imposed by the foreground mass emerges clearly from the statistical noise. Unlike strong lensing, weak lensing requires no special alignment at all. It works for any mass, anywhere, as long as there are enough background galaxies to measure. Applied not to a single foreground cluster, but statistically across an entire survey of sky, the same principle produces what astronomers call cosmic shear, a faint, coherent distortion pattern imprinted on background galaxies by every clump of matter, visible or dark, that their light happens to pass on its way to Earth. Measuring cosmic shear across large enough patches of sky lets cosmologists reconstruct not just the mass of one cluster, but the entire three-dimensional distribution of matter across a significant fraction of the observable universe, without ever needing a dramatic merging collision to make the signal visible. Strong lensing, the dramatic multiple image case Zwicky originally predicted, has found an entirely unexpected second use in recent years. When a distant quasar's light is split into several images by a foreground galaxy, the different light paths are not exactly the same length, because gravity bends some paths more sharply than others. Light traveling the more sharply bent path arrives at Earth slightly later than light traveling the gentler one, a delay that can stretch to days or even weeks. easily measurable if the quasar happens to flicker in brightness, since the same flicker shows up in each image at a slightly different time. A collaboration of astronomers used exactly this time delay, measured across several lensed quasars, combined with a detailed model of the lensing galaxy's mass, to calculate an independent estimate of the Hubble constant, the rate at which the universe is expanding today. It is a strange, roundabout way to measure something as fundamental as the universe's expansion rate, using nothing but the arrival times of light bent around a foreground galaxy, and it depends entirely on correctly modeling how much dark matter that foreground galaxy contains. The most famous single application of this technique came in 2006, with observations of a merging pair of galaxy clusters that astronomers nicknamed the bullet cluster, for the way one smaller subcluster appears to have punched clean through a larger one, like a bullet through a target. The smaller subcluster passed through the larger main cluster at a speed of roughly 4,700 kilometers per second, and the collision itself happened somewhere between 100 and 200 million years ago. We are watching the aftermath. When two clusters of galaxies collide, the galaxies themselves pass through one another almost entirely undisturbed, because the space between individual galaxies is so vast that a direct collision between any two stars is essentially impossible. The hot gas filling the space between those galaxies behaves very differently. It collides, experiences drag, and slows down, separating from the galaxies that carried it. X-ray images of the aftermath, taken by the Chandra X-ray Observatory, show exactly that. A bright, shock-heated bridge of gas caught between the two clusters, lagging noticeably behind the galaxies on either side. A team led by Douglas Clow and Maxim Markovich used the Hubble Space Telescope, along with ground-based telescopes in Chile, to map the total mass distribution across the collision using weak gravitational lensing. If dark matter were not a separate substance from the ordinary gas, if all the missing mass really were simply hot, hidden gas, then the reconstructed gravity map should trace the X-ray gas closely. It did not. The lensing map showed the bulk of the mass sitting with the galaxies themselves, offset from the shock-heated gas trailing behind. The invisible mass had passed straight through the collision alongside the galaxies, essentially undisturbed, while the ordinary gas had been slowed and left behind by the drag of the encounter. The resulting image, X-ray gas rendered in one color, lensing-derived mass contours rendered in another, visibly offset from each other, became one of the most widely reproduced images in modern cosmology, cited by many as close to direct, physical proof that dark matter behaves as a separate, collisionless substance rather than merely a modification of how gravity works. It would be dishonest to present the bullet cluster as closing every argument. Advocates of modified gravity theories have proposed that the offset could still be explained, in a relativistic extension of their models, by invoking massive neutrinos or some other dim, baryonic component alongside a modified force law. The debate over exactly how much weight the bullet cluster carries against alternatives to particle dark matter continues in the technical literature. But the simplest, most direct interpretation that dark matter is a genuine, collisionless substance, separable from ordinary gas under the right conditions, explains the observation naturally and quantitatively, without any additional assumptions. Since that first result, similar merging clusters have been studied the same way. One, nicknamed the baby bullet, shows a comparable offset between mass and gas. Another, sometimes called the train wreck, initially appeared to show a dark concentration with no associated galaxies at all, a genuine puzzle, though later, more careful analysis suggested the apparent dark core was likely an artifact of the complex geometry involved in reconstructing the lensing signal for that particular system, a useful reminder that individual collisions can be messy, and that interpreting any single lensing map requires real care. What these results establish, taken together, is that dark matter can be weighed and mapped directly, without any assumption about what it is actually made of. The technique Zwicky proposed on paper in 1937, decades before the technology existed to carry it out, has become a routine tool of modern cosmology, used not only on dramatic colliding clusters, but across enormous surveys of the entire sky. The Dark Energy Survey mapped weak lensing signals across roughly an eighth of the sky. A newer European mission called Euclid, launched to study precisely this kind of large-scale structure, is now extending that map across a much greater portion of the heavens, with a resolution and depth no earlier survey has matched. Lensing confirms, independently of rotation curves and independently of cluster dynamics, that the dark halos are real, that they are massive, and that they can be separated from ordinary matter in the most violent collisions the universe has to offer. But weighing the invisible is not the same as identifying it. Lensing tells us where the mass sits. It does not tell us what the mass is made of. For that, the story has to go further back, still beyond galaxies, beyond clusters, all the way to the oldest light in the universe, a glow released when the cosmos was only 380,000 years old, carrying within its faint pattern of hot and cold spots something close to the exact recipe of everything that exists. That light is the cosmic microwave background. It is the oldest light we will ever be able to see. The story of its discovery has an odd shape, because the theoretical prediction came first, was published clearly, and was then almost entirely forgotten for 16 years. In 1948, two physicists working under George Gamow, the same George Gamow who would later supervise Vera Rubin's doctoral work, calculated what the early universe's leftover radiation should look like today, after billions of years of cosmic expansion had stretched and cooled it. Ralph Alpher and Robert Herman worked through the physics of the hot early universe and arrived at a specific, testable number, a faint background glow, uniform across the whole sky, cooled by cosmic expansion down to roughly 5 degrees above absolute zero. It was a genuinely remarkable prediction, rigorously derived, published in a real scientific journal, and it was almost completely ignored. No one built an instrument to look for it. The paper went uncited for years. Cosmology in the 1950s was a small field, resources were scarce, and a prediction of an almost imperceptibly faint microwave hiss, uniform in every direction, simply did not register as an experiment worth funding. It sat quietly in the literature, forgotten, while the universe kept glowing exactly as Alpha and Herman said it would. The rediscovery, when it finally came in 1964, happened entirely by accident, and to a team who did not know the prediction existed. Arno Penzias and Robert Wilson at Bell Labs in New Jersey were testing a sensitive microwave antenna originally built for satellite communications, and they kept finding a faint, persistent hiss of noise they could not eliminate, no matter what they tried. They checked the wiring, they checked the electronics, they even climbed into the horn antenna itself and cleared out pigeon droppings, suspecting the birds nesting inside might be the source. The noise remained, identical in every direction they pointed the antenna, day or night, summer or winter. Only when they mentioned their frustrating, uneliminable signal to colleagues did word reach a team of physicists at Princeton, led by Robert Dick, who had independently begun building an instrument specifically to search for exactly this radiation, apparently without ever having come across Alpha and Herman's 16-year-old prediction either. When Dickey's team realized what Penzias and Wilson had stumbled onto, Dicker turned to the colleagues in his own lab and said simply, "We've been scooped." Penzias and Wilson received the Nobel Prize in Physics in 1978 for a discovery they made without initially understanding what they had found. A genuinely strange, layered story of prediction, forgetting, and rediscovery spanning 16 years and two entirely separate research groups who never quite crossed paths until the very end. The early measurements of this glow showed it to be almost perfectly uniform across the sky, the same temperature in every direction to within a fraction of a percent. But almost perfectly uniform is not perfectly uniform, and the tiny deviations from that uniformity are the key to everything that follows. A completely smooth early universe would never have produced galaxies at all. Gravity needs some initial seed, some slight overdensity, to begin pulling matter together. The cosmic microwave background had to contain faint temperature fluctuations, corresponding to the same faint density fluctuations that would eventually seed all cosmic structure. Detecting them required an instrument sensitive enough to measure temperature differences of only a few parts in 100,000, spread across the entire sky. That instrument was the Cosmic Background Explorer, a satellite launched by NASA in 1989. Its detector mapped the whole sky and found the fluctuations for the first time, announcing the result in April of 1992. The lead scientist on the mission, John Mather, presented a map of the tiny hot and cold spots to a packed meeting of the American Physical Society, and the room rose in a standing ovation. Stephen Hawking called it the most important discovery of the century, if not of all time. The fluctuations were real, and they were, quite literally, the seeds of every galaxy that would ever form. That first map was blurry, its resolution smeared detail across patches of sky many times wider than the full moon. Resolving the individual peaks and valleys in finer detail required a new generation of instruments. The Wilkinson Microwave Anisotropy Probe, a NASA satellite launched in 2001, improved the resolution dramatically, sharp enough to begin extracting precise cosmological numbers from the pattern. The European Space Agency's Planck satellite, launched in 2009, pushed the measurement to its practical limit, mapping the entire sky with a resolution of only a few arc-minutes and a temperature sensitivity almost too small to describe in ordinary terms. Its final data release, in 2018, produced the most precise accounting of the universe's contents ever obtained. There is a further layer to this story worth telling honestly, because it captures something important about how careful this kind of science has to be. The temperature fluctuations in the cosmic microwave background are not the only signal cosmologists have gone looking for in that ancient light. Theorists predicted that gravitational waves generated during the universe's earliest fraction of a second, a hypothesized period of extraordinarily rapid expansion called inflation, should leave a distinctive, swirling pattern of polarization in the microwave background, a signature known as a B-mode pattern. In March of 2014, a team working with a South Pole-based instrument, part of a series of experiments known as BICEP, announced they had detected exactly this signature at a strength stronger than most theorists had expected. It was treated, briefly, as one of the great discoveries in the history of cosmology, direct evidence of gravitational waves from the first fraction of a second after the Big Bang. Within months, further analysis, aided by new data from the Planck satellite, showed that the signal could be explained entirely by polarized light, scattered from ordinary dust within our own galaxy, sitting directly in the line of sight, rather than by any primordial gravitational wave at all. The announcement was quietly, honestly retracted. It stands as one of the clearer recent examples of science correcting itself in public, a genuinely exciting result that did not survive further scrutiny. Acknowledged as such rather than defended past the point the evidence would support. The search for that particular signature continues today, with more careful control for foreground dust, and no confirmed detection has yet been made. There is one more unresolved feature of the cosmic microwave background worth naming honestly, because it has never been fully explained and it is not connected to dust or any known instrumental error. Buried in the Wilkinson probe's map of the sky is an unusually large, unusually cold region, roughly 10 degrees across, cooler than its surroundings by an amount that is difficult to produce through ordinary statistical variation alone. Astronomers call it, plainly, the cold spot. Several explanations have been proposed. It might simply be an unusually large statistical fluctuation, rare but not impossible in a universe as vast as ours. It might correspond to an enormous, largely empty region of space, a supervoid, lying between us and that patch of ancient light, its lack of matter causing microwave photons passing through it to lose slightly more energy than photons traveling through more typical regions. Deep galaxy surveys of the region in the direction of the cold spot have found tentative evidence of exactly such a supervoid, though its size and depth remain debated, and it is not entirely clear the void alone is large enough to produce the full effect observed. It remains, honestly, one of the odder loose threads in an otherwise extraordinarily well-explained sky. To understand how a map of ancient microwave light can tell us anything about dark matter at all, it helps to understand what the hot and cold spots actually represent. They are not random noise. They are the frozen imprint of the acoustic oscillations described earlier in this story, sound waves that rippled through the primordial plasma before recombination, driven by the competing pull of gravity and the outward push of trapped radiation. A region slightly denser than average would begin to collapse under gravity, be pushed back apart by radiation pressure, collapse again, and oscillate in this way for as long as the plasma phase lasted. The moment recombination arrived and the photons streamed free, whatever phase of that oscillation each region happened to be in at that instant was frozen permanently into the pattern of the sky. A region caught at maximum compression became a hot spot. A region caught at maximum rarefaction became a cold spot. Everything in between shows up as an intermediate temperature. Analyzing the cosmic microwave background means constructing what is called a power spectrum, a graph showing how much fluctuation exists at each angular scale across the sky. At large scales, the spectrum is nearly flat. Then it rises into a series of distinct peaks. The acoustic peaks, representing the fundamental frequency of the primordial sound waves and its overtones. The position of the very first peak reveals the overall geometry of the universe, and it shows the geometry to be flat, that the angles of an enormous cosmic triangle add up to exactly 180 degrees, just as they would on an ordinary flat sheet of paper. The relative heights of alternating peaks reveal the baryon density, since ordinary matter, having genuine mass, enhances the compressive half of each oscillation more than the rarefied half. And the third peak in particular is unusually sensitive to the density of dark matter, because dark matter contributes gravity to the oscillation without ever contributing any of the radiation pressure that pushes back against it, deepening the gravitational wells the plasma oscillates within. The Planck satellite measured the first 7 acoustic peaks with extraordinary precision, and fitting that entire pattern with a standard cosmological model produces a small set of numbers that now function as the bedrock of modern cosmology. Ordinary matter makes up about 5% of the universe's total energy content. Dark matter makes up roughly 27%. Dark energy accounts for the remaining 68% or so, expressed as a fraction of matter alone rather than of the total energy budget. Dark matter constitutes something close to 85% of everything with mass in the universe. The same figure this story opened with, now arrived at through an entirely independent measurement of ancient light, rather than through the motion of stars or the bending of light around galaxies. It is worth pausing to close off one tempting possibility that this precision rules out. The known neutrinos, genuine, confirmed particles, produced in staggering numbers by the Sun and by the Big Bang itself, do have mass, we now know, and they do not interact with light. For a while they looked like an obvious dark matter candidate hiding in plain sight, requiring no new physics at all. But the cosmic microwave background, combined with large surveys of how galaxies cluster, places a tight upper limit on how much total mass all the neutrinos in the universe can carry. And that limit is far too small. The neutrinos simply do not add up to anywhere near the required amount. They contribute something, a faint background of mass threading through everything, but they account for only a tiny fraction of the dark matter total. And because they move fast, they belong to the hot dark matter category already ruled out as the dominant component. The particle that would have been most convenient, because we already know it exists, turns out to be present in the wrong amount and moving at the wrong speed. Dark matter has to be something else, something not yet found in any collider or detector on Earth. These numbers hold up under cross-examination. The baryon density derived from the cosmic microwave background matches closely, The baryon density derived from Big Bang nucleosynthesis, two completely independent methods, one measuring sound waves in the early universe, the other measuring nuclear reactions in the universe's first 3 minutes, converging on the same answer from opposite directions. Whatever dark matter is, it is not made of protons and neutrons. It is not any particle known to interact with light. It is not anywhere on the periodic table. It is something else entirely. The cosmic microwave background also tells us something about how dark matter moves. If it had been hot traveling close to the speed of light in the early universe, the way neutrinos do it would have streamed freely out of small overdensities almost as fast as they formed, erasing the seeds of small-scale structure before they could grow. The observed power spectrum rules this out. Dark matter must have been cold, or at most modestly warm, moving slowly enough in the early universe to clump and form the halos we see clear evidence for today. This is what the oldest light in the universe can tell us. How much dark matter exists, that it cannot be ordinary matter, and that it must have been cold. What it cannot tell us, with all its extraordinary precision, is what dark matter actually is. It gives us the recipe. It does not give us the identity of the main ingredient. The question of that identity carries the story from the oldest light in the universe to the deepest places on Earth. But before physicists turned underground to search for an exotic new particle, the more conservative possibility had to be checked first, that the dark matter halo was simply made of ordinary matter, hiding in a dim, compact, and thoroughly unglamorous form. Brown dwarfs failed stars too small to sustain the nuclear fusion that powers a true star, along with rogue planets, cold white dwarfs, and other faint compact objects, could, in principle, account for some or all of a galaxy's missing mass without requiring any new physics whatsoever. Astronomers gave these hypothetical objects a name, MARCOs, for massive compact halo objects, deliberately playing off the acronym WIMP that was already in use for the competing particle hypothesis. 2 independent survey collaborations set out in the 1990s to test the idea directly, using gravitational microlensing, the same brightening effect later used to search for primordial black holes to look for compact objects drifting through the Milky Way's halo. The American-led MACO project and the French EROS collaboration each monitored millions of stars in the Large Magellanic Cloud for years, watching for the brief, characteristic brightening a passing compact object would produce as its gravity focused the light of a background star. Both surveys found a small number of genuine microlensing events, confirming that some compact objects really do exist in the halo, but the number of events was far too small to account for more than a modest fraction of the halo's total mass. By the early 2000s, the combined results had effectively closed the door on ordinary compact objects as the primary explanation for dark matter. Whatever the missing mass is made of, it is not, in the main, brown dwarfs, rogue planets, or any other dim but ordinary object built from protons and neutrons. That left the exotic particle hypothesis as the leading remaining possibility, and it is what sent physicists underground. If dark matter is a particle, as the cosmic microwave background strongly implies, then physicists needed to find out what kind. For more than 40 years, they have pursued the answer by building detectors in laboratories buried deep underground, hoping that a single dark matter particle, passing silently through the Earth the way it passes through everything else, might occasionally strike a single atomic nucleus and leave behind a trace. Consider, for a moment, what is passing through you as you lie there. If the leading models are right, the dark matter in the Milky Way's halo is streaming through the room at something like 230 kilometers per second, the speed at which the sun plows through the surrounding halo on its orbit around the galactic center. At that speed, a steady flux of dark matter particles is crossing your body every second, the exact number depending on how heavy each particle turns out to be. But for a typical candidate, something on the order of billions, passing through a space the size of your hand every second. They do not push you. They do not warm you. They register on none of your senses and none of your instruments, In the entire span of your life, statistically, perhaps one of these countless particles might interact with a single atom somewhere in your body, and even that is uncertain, and you would never know. You are, at this moment, almost perfectly transparent to the substance that makes up most of the matter in the universe. It moves through you the way light moves through glass, except that glass, at least, bends the light a little. To dark matter, you are not even glass. You are empty space with a faint gravitational field, and it falls through you and out the other side and keeps going, out through the far wall, down through the rock, through the molten core of the earth, and back out into the dark on the other side of the planet, without slowing down. To catch even one of them, deliberately, you would have to build something extraordinary. The leading candidate for most of those 4 decades has been a class of particles called WIMPs, an acronym for Weakly Interacting Massive Particles. A WIMP is a hypothetical particle with a mass somewhere between 10 and 1,000 times that of a proton, interacting with ordinary matter only through the weak nuclear force and through gravity. The weak force operates only at extraordinarily short range and is easily overwhelmed by the much stronger electromagnetic and nuclear forces, meaning a WIMP could, in principle, pass through a light year of solid lead with only a small chance of ever touching anything. But the Milky Way's dark matter halo is thought to contain enormous numbers of these particles, and if a detector is large enough and patient enough, one of them might eventually strike a nucleus and cause it to recoil a tiny event, depositing only a few thousand electron volts of energy, producing a faint flash of light or a small pulse of electrical charge that a sufficiently sensitive instrument could, in principle, register. The WIMP idea had a genuinely elegant theoretical motivation behind it. In the 1980s and 90s, particle physicists were developing a broader theory called supersymmetry, proposing that every known particle has a heavier, undiscovered partner. The lightest of these hypothetical partners, called the neutralino, would be stable, electrically neutral, and massive, exactly the properties needed for a dark matter candidate. Even more strikingly, calculations showed that a particle with roughly these properties would naturally have been produced in the early universe, in almost precisely the abundance needed. To account for the dark matter density later measured by the cosmic microwave background, a coincidence so clean that physicists nicknamed it the WIMP miracle, and many considered it too elegant not to be true. The Large Hadron Collider at the European Organization for Nuclear Research was expected to produce supersymmetric particles directly. Underground detectors were expected to catch WIMPs colliding with atomic nuclei. Telescopes searching the sky for gamma rays were expected to see the faint signature of WIMPs annihilating with one another out in space. It was a coherent, mutually reinforcing research program, and it drew a generation of physicists underground to wait. The detectors had to be built underground because the signal they were chasing is extraordinarily faint, and the surface of the Earth is bathed in overwhelming background noise. Cosmic rays constantly bombard the atmosphere, producing showers of secondary particles that would swamp any genuine dark matter signal many times over. Deep rock shields against this. The Gran Sasso National Laboratory in Italy sits beneath 1,400 meters of the Apennine Mountains. The Sanford Underground Research Facility in South Dakota occupies a former gold mine, 1.5 kilometers below the surface. Facilities in Japan and Canada are built inside mountains and active mines respectively, chosen specifically for the sheer thickness of rock standing between the detector and the noisy surface world above. The leading detector technology uses liquid xenon, a chemically inert noble gas that becomes a transparent liquid at temperatures around -100 degrees Celsius. When a particle strikes a xenon nucleus, it produces 2 distinct signals: an initial flash of ultraviolet light and a cloud of freed electrons that drift upward under an electric field before producing a second flash in a layer of gas above the liquid. Comparing the ratio of these 2 signals lets researchers distinguish a nuclear recoil, the expected signature of a heavy, slow-moving WIMP from an electron recoil, the far more common signature produced by ordinary background radiation. The discrimination is not perfect, but it is powerful enough to suppress the background by many orders of magnitude, isolating a small number of genuinely unexplained events for careful analysis. The experiments themselves carry names that sound almost like science fiction: XENON, Lux, Panda X, CREST, and a cryogenic germanium experiment known as the cryogenic dark matter search. Each successive generation has grown larger and more sensitive than the last. An early version of the xenon experiment, using roughly a ton of liquid xenon at the Gran Sasso laboratory, gave way to a much larger successor using several tons. The Lux Zeppelin experiment at the Sanford facility in South Dakota now uses 7 tons of liquid xenon and stands as the most sensitive WIMP search operating anywhere in the world. Every one of these detectors is wrapped in layers of shielding water tanks to catch and veto stray muons passing through, lead and copper to absorb background gamma rays, and painstaking screening of every single component used in construction, since even a speck of dust carrying a trace of natural radioactivity can produce a background event convincing enough to mimic a genuine signal. Building one of these instruments takes years and costs tens of millions of dollars. The obsession with cleanliness reaches strange and specific extremes. Ordinary lead, freshly smelted, carries a faint radioactive isotope of its own, lead-210, which decays slowly over roughly 2 decades and produces exactly the kind of background these detectors are built to eliminate. The only way to obtain lead free of that isotope is to find lead old enough that the isotope has already decayed away, which is why some experiments have gone to the extraordinary length of sourcing ancient Roman lead recovered from shipwrecks that sank 2,000 years ago. Its radioactivity long since faded to near nothing after 20 centuries at the bottom of the sea. Ingots cast by Roman metalworkers, lost in a storm before the birth of the modern calendar, now sit at the heart of instruments designed to detect the most elusive substance in the universe. There is something quietly strange about that, the deep past and the deep future of physics meeting inside a shielded tank a mile underground. The work itself is a particular kind of patient. Physicists descend each day, often by the same cage lifts that once carried gold or nickel miners into the same rock, into laboratories where the temperature and humidity are held constant and the air is filtered obsessively, and where the primary activity, day after day, is waiting. The detectors run continuously, for years at a stretch, recording essentially nothing, the whole enterprise organized around the possibility that, on some unpredictable night, a single nucleus, somewhere in 7 tons of liquid xenon, will recoil in a way that cannot be explained by any known background. It is among the most patient forms of science ever practiced. Careers measured against the possibility of a single decisive event that may never come, and they have seen nothing. Year after year, each new round of results pushes the exclusion limits further down. The allowed cross-section for a WIMP interacting with an atomic nucleus, essentially, a measure of how likely such a collision would be, has been driven down by orders of magnitude, generation after generation of detector, until much of the parameter space where the simplest, most naturally motivated WIMP models were expected to live is now almost entirely ruled out. The most recent results from the Lux Zeppelin experiment, released in 2024, found no evidence whatsoever for dark matter particles, setting the strongest limits achieved anywhere to date. There has been exactly one persistent claim of a genuine signal, and it deserves to be told honestly, contradictions and all. An experiment called Dharma, run in collaboration with a successor detector called Libra at the Gran Sasso laboratory, uses crystals of sodium iodide rather than liquid xenon and has reported, for more than 20 years running, a seasonal rise and fall in its event rate that repeats reliably, year after year. This is exactly the pattern a genuine dark matter signal should produce, a phenomenon the theoretical physicist Catherine Fries had worked out in detail years before any detector was sensitive enough to look for it. As the Earth orbits the Sun, its velocity relative to the surrounding dark matter halo changes with the seasons, adding to the Sun's own motion through the galaxy in one half of the year and partially cancelling it in the other, producing a small but measurable seasonal modulation in the expected collision rate in effect, a faint dark matter wind that should blow slightly harder against the Earth at some times of year than at others. The Dharma and Libra collaboration has reported exactly this pattern. At a statistical significance exceeding 12 standard deviations, and insists the signal represents real dark matter. The trouble is that no other experiment, using any detector technology, has ever been able to reproduce it. The xenon-based experiments, the germanium-based experiments, every other detector searching in the same region of parameter space, see nothing where the Dharma and Libra result would predict a clear signal. The most likely explanation is some unmodeled seasonal background, perhaps a seasonal shift in cosmic ray muon flux or ambient radon levels that happen to track the temperature of the seasons rather than genuine dark matter. The collaboration has not released its raw data for full independent analysis, and most of the wider physics community has quietly moved on. But the experiment continues running, its signal continues to modulate on schedule, and it remains, honestly, an unresolved anomaly rather than a closed case. The absence of any confirmed WIMP signal, paired with the failure of the Large Hadron Collider to find any evidence of supersymmetric particles at all, has produced what some physicists now openly call the WIMP crisis. The theoretical motivation that once made the WIMP the obvious, elegant candidate has weakened considerably, and the available parameter space keeps shrinking. This does not mean WIMPs are entirely ruled out. There remain mass ranges, both lighter and heavier than the classic sweet spot, that current detectors still struggle to probe effectively. But there is a hard limit approaching, that the field has known about for years and is now beginning to reach. As detectors grow larger and more sensitive, they eventually become sensitive enough to detect not dark matter, but neutrinos, the flood of ordinary neutrinos streaming from the Sun and from distant cosmic events, which occasionally strike a nucleus in exactly the way a dark matter particle would, producing an essentially identical signal. This threshold is called the neutrino floor, and once a detector reaches it, distinguishing a genuine dark matter signal from the irreducible background of neutrino collisions becomes extraordinarily difficult. The next generation of experiments, with proposed names like Darwin, is designed to push right up against that floor, using tens of tons of liquid xenon. If dark matter still does not appear even there, the classic WIMP will not merely be disfavored, it will be, for practical purposes, cornered against a wall beyond which direct detection of that kind cannot easily go. The era of confident expectation that a detector would eventually catch one has clearly ended, and the field of dark matter physics has broadened considerably in response. Direct detection, waiting underground for a particle to strike a nucleus, has not been the only strategy. A separate approach, called indirect detection, searches instead for the products that WIMPs should leave behind if two of them ever collide and annihilate each other out in space, a process expected to produce a distinctive flood of gamma rays wherever dark matter is densest. NASA's Fermi Gamma Ray Space Telescope, surveying the sky continuously since 2008, found something intriguing near the center of the Milky Way, an excess of gamma rays above what known astrophysical sources could easily explain, glowing from roughly the right region and with roughly the right energy spectrum to match a dark matter annihilation signal. For several years after it was first reported, the galactic center excess was treated as one of the more promising indirect hints of dark matter anywhere in the sky. Closer analysis has complicated that picture considerably. The spatial pattern of the excess, mapped in increasing detail, looks less smooth and more clumpy than a genuine dark matter halo should produce, and it now appears to trace the positions of old, faint stellar populations unusually closely. Most researchers in the field currently consider the excess more likely to come from a large, undetected population of rapidly spinning neutron stars called millisecond pulsars, too faint individually to be picked out one by one, but numerous enough collectively to produce exactly this kind of diffuse gamma-ray glow. It has not been fully ruled out as a dark matter signal, and the debate continues in the technical literature. But it stands today as another example of a promising anomaly that careful, patient scrutiny has made look considerably less certain than it first appeared. Precisely the kind of honest walking back that distinguishes a field doing real science from one simply chasing headlines. Other candidates have moved into the space the WIMP once occupied almost alone. The axion, a hypothetical particle first proposed to solve an entirely unrelated problem in the physics of the strong nuclear force, has become a leading alternative. The problem it was invented to solve is worth a moment, because it shows how a particle can be motivated by pure theory long before anyone thinks of it as dark matter. The strong nuclear force, which binds quarks together inside protons and neutrons, could in principle violate a deep symmetry of physics. It could behave slightly differently for particles and their mirror image antiparticles. Every experiment ever performed shows that it does not, to an astonishing degree of precision. Nothing in the theory requires this. The symmetry could have been broken by any amount, and instead it is preserved almost perfectly, for no obvious reason. This is called the strong CP problem, and in 1977 the physicists Roberto Peccei and Helen Quinn proposed an elegant solution, which naturally implied the existence of a new, extremely light particle. Frank Wilczek and Steven Weinberg independently worked out the properties of that particle shortly after, and Wilczek gave it its name, the axion, after a brand of laundry detergent, because it cleaned up a problem. Only later did physicists realize that a particle with exactly these properties, produced in the right way in the early universe, would also make an excellent dark matter candidate. Abundant, stable, electrically neutral, and cold. It was invented to fix a symmetry problem in nuclear physics and turned out, as a bonus, to fit the dark matter role almost perfectly. Axions would be extraordinarily light, trillions of times, lighter than an electron, and would not produce anything like a nuclear recoil. Instead, in the presence of a sufficiently strong magnetic field, an axion is predicted to occasionally convert directly into a photon. The axion dark matter experiment at the University of Washington uses a resonant microwave cavity inside a powerful magnet, tuned slowly across a wide range of possible axion masses, listening for the faint signature of that conversion. It has been running since the 1990s, steadily excluding mass ranges and coupling strengths as it goes. No axion has been detected yet, but unlike the WIMP search, the axion hunt is still in its earlier stages, with much of its theoretically favoured territory yet to be explored. Newer instruments have joined the search in recent years: the haloscope at Yale sensitive to axion cold dark matter experiment, generally known simply as HAYSTACK, and the Center for Axion and Precision Physics Research in South Korea, both using variations on the same resonant cavity principle, tuned to different, complementary slices of the possible axion mass range. Each new instrument narrows the remaining territory a little further in a search that, unlike the WIMP hunt, has not yet reached the point of a genuine crisis of confidence. Sterile neutrinos, a heavier, still more reluctant cousin of the known neutrino species, have also been proposed as dark matter candidates. Space telescopes sensitive to X-rays have searched galaxy clusters for the faint emission line that a decaying sterile neutrino would be expected to produce. A handful of tentative signals have been reported over the years, and most have faded under closer scrutiny with deeper, more careful observation. The picture here remains genuinely unsettled. The failure to find a WIMP and the persistent, nagging success of an entirely different idea on smaller scales have together pushed the most serious alternative to particle dark matter back into the center of the conversation. That alternative began in the early 1980s. in the mind of an Israeli physicist named Mordechai Milgrom. Milgrom was working, at the time, as a relatively junior researcher, and he was not setting out to overturn a century of established physics. He was simply looking closely at galaxy rotation data and noticing a pattern that the standard dark matter picture did not obviously predict, but that the observations seemed to demand on their own terms. In galaxy after galaxy, the point where a rotation curve departed from the ordinary Newtonian prediction was not tied to any particular radius or any particular type of galaxy. It was tied, consistently, to a specific acceleration, a threshold below which Newtonian gravity, applied straightforwardly, simply stopped matching what was observed. That threshold, which came to be called a naught, works out to about 1.2 times 10 to the power of minus 10 meters per second squared. An almost unimaginably small acceleration, roughly what you would feel from the gravitational pull of a single grain of sand held a meter from your hand. And yet it appeared to behave as a genuine universal constant, showing up again and again across galaxies of wildly different sizes and luminosities. Milgrom's proposal was simple to state and audacious in its implications. Rather than adding an unseen mass to explain the flat rotation curves, change the law of gravity itself at very low accelerations. In ordinary Newtonian physics, gravitational force falls off with the square of the distance moved twice as far from a mass, and the pull weakens to a quarter of its original strength. Milgrom proposed that below the threshold acceleration a0, gravity instead falls off in direct proportion to distance alone, a much gentler decline that naturally produces exactly the kind of flat rotation curve Rubin and Bosma had measured. He called the resulting theory modified Newtonian dynamics, or MOND. Milgrom published 3 papers, laying out the idea in 1983, and the reception, unsurprisingly, was cool. Proposing to rewrite one of the best-tested laws in the whole of physics, on the strength of galaxy rotation data alone, struck most of his colleagues as a far less plausible move than simply adding an unseen form of matter to a law that had otherwise worked flawlessly for 3 centuries. For years, MOND remained a minority pursuit, kept alive largely through Milgrom's own persistence, and a small number of collaborators willing to keep testing it against new data as better rotation curves became available. What makes MOND genuinely striking, and what has kept it in serious scientific conversation for more than 4 decades, is that it works for individual galaxies using a single, fixed constant. Astronomers do not need to tune a naught separately for each galaxy studied. Set the value once, from the data, and the same modified force law reproduces the observed rotation curve for galaxy after galaxy, hundreds of them, spanning giant spirals down to faint dwarfs, using nothing but the distribution of visible matter alone, with no additional free parameters required. A theory built around one universal constant that fits hundreds of independent systems this cleanly is the kind of result that tends to hold a physicist's attention, whatever their prior commitments. MOND also makes a genuine prediction about a well-known relationship in astronomy called the Tully-Fisher relation, which connects a spiral galaxy's total luminosity to how fast it rotates. Brighter galaxies rotate faster, following a remarkably tight pattern with very little scatter. In the standard dark matter picture, this relationship emerges only indirectly, through a complicated interplay between how galaxies form, how gas cools, and how dark matter halos assemble. Simulations can approximately reproduce the pattern. But there is no simple, direct reason built into the theory for why it should be quite this tight. In MOND, the Tully-Fisher relation falls directly out of the mathematics, as a genuine prediction rather than an emergent coincidence. This has been sharpened considerably in recent years. In 2016, the astronomers Stacy McGarr, Federico Lelli, and James Schombert published what they called the radial acceleration relation, drawn from careful rotation curve measurements across more than 150 galaxies of every type. They found that the observed gravitational acceleration inside a galaxy at any given radius can be predicted almost perfectly from the distribution of visible matter alone, following a single universal relationship remarkably close to what Milgrom's original proposal from the 1980s had anticipated. Magar, in particular, has become one of the most persistent and rigorous public advocates for taking this tension seriously, arguing that any complete theory of dark matter eventually has to explain why visible matter alone predicts galactic dynamics. This is precisely something the standard cold dark matter picture, for all its successes elsewhere, still has not fully explained. But MOND is not a complete theory of the universe, and its problems are severe enough that most cosmologists remain unpersuaded. The most fundamental issue is that MOND, in its original form, is a non-relativistic modification of Newtonian gravity, while the universe itself is thoroughly relativistic. A full cosmological theory needs to describe not just galaxy rotation, but the expansion of the universe, the cosmic microwave background, gravitational lensing, and the behavior of gravitational waves, all of which require a relativistic framework that Milgrom's original proposal simply does not provide on its own. Attempts to build a fully relativistic version have been made, most notably a theory called tensor vector scalar gravity, developed by Jacob Bekenstein in 2004, which reduces to ordinary MOND in the appropriate limit, but requires considerably more mathematical machinery than general relativity itself, and has struggled to reproduce the full range of cosmological observations with the same precision. The most damaging challenge for MOND comes from galaxy clusters rather than individual galaxies. Even applying the modified force law, the visible mass in a cluster still falls short of what is needed to explain the observed gravity. Not by the factor of 5 typical in the standard dark matter picture, but by roughly a factor of 2, which MOND advocates have generally attributed to ordinary or sterile neutrinos, rather than to any modification of gravity. This is an uncomfortable concession for a theory whose original appeal was eliminating the need for unseen mass altogether, and the bullet cluster, discussed earlier in this story, remains a serious problem for MOND specifically, because it requires a genuine, collisionless mass component separate from the ordinary gas, precisely the kind of substance a pure modification of gravity cannot, on its own, provide. MOND advocates have responded by invoking sterile neutrinos to explain the bullet cluster as well, which again concedes much of the ground the theory originally hoped to hold. The cosmic microwave background poses perhaps the hardest test of all. The standard cold dark matter model fits the full pattern of acoustic peaks with only 6 parameters, and the fit is extraordinarily precise, while relativistic versions of MOND require additional parameters and still struggle to match the height of the third peak and the shape of the spectrum's damping tail at the same time. For all of these reasons, MOND remains a minority position. Most cosmologists continue to regard dark matter as a genuine substance, rather than a signal that gravity itself needs revising. But the fact that MOND works this well for individual galaxies in some respects more cleanly than dark matter models, which must fine-tune halo properties to reproduce the same Tully-Fisher relation MOND predicts outright, is a real and unresolved puzzle. It may be coincidence. It may be telling us something deep about how galaxies form within dark matter halos, some feedback process that imprints Milgrom's acceleration scale onto the visible matter without requiring any change to gravity itself. Or it may be a genuine clue that our theory of gravity is incomplete in some way not yet understood. A more recent test has added fresh fuel to the debate, rather than settling it. Wide binary star systems, pairs of stars orbiting one another at such enormous separation that their mutual gravitational acceleration falls below Milgrom's threshold, a naught entirely within the Milky Way itself, far from any galaxy's outer edge offer, in principle, a clean laboratory for testing whether gravity truly behaves differently at low acceleration. In 2023, the astronomer Kyu-Hyun Che analyzed the orbital motions of thousands of these wide binary pairs, drawn from the exquisitely precise positions and motions measured by the Gaia satellite, and reported that their orbital speeds matched the MOND prediction more closely than the standard Newtonian one. The result has been contested. Other researchers have raised concerns about how cleanly wide binaries can be selected from Gaia's data, and how sensitive the analysis is to contamination from unrelated stars that merely appear close together on the sky. The debate over wide binaries is, as of this telling, still actively unresolved. The honest position is to hold all of these possibilities open at once, and to acknowledge plainly that the debate is not fully settled. The persistent puzzle MOND presents, alongside the WIMP's continuing silence, has pushed the theoretical landscape wider still. One idea gaining serious attention is the possibility of an entire dark sector. The notion that dark matter is not a single particle at all, but a whole hidden realm of particles and forces, potentially as rich and complex as the visible universe we already know. Just as ordinary matter contains electrons, protons, photons, and a whole zoo of other particles governed by several distinct forces, a dark sector might contain multiple species of dark particle, interacting through forces entirely their own, forces that never touch ordinary matter at all except through gravity. The idea has a specific, well-developed proposal behind it. In 2000, the physicists David Spergel and Paul Steinhardt suggested that dark matter particles might interact with each other through some force entirely separate from the ones that govern ordinary matter, strongly enough to collide and scatter on the scale of individual galaxies, while still behaving as effectively collisionless on the much larger scale of colliding galaxy clusters like the Bullet Cluster. Such self-interactions could allow dark matter particles to collide and scatter off one another, which would help smooth a sharp central cusp into the flatter cores sometimes observed in dwarf galaxies. They could, in principle, allow dark matter to bind into structures of its own dark atoms, even dark stars, entirely invisible to any instrument built from ordinary matter. This is not yet a tested theory. It is a framework for disciplined speculation, constrained only by the requirement that nothing in the dark sector produce an effect that contradicts what we already observe. It is also, in its own way, a humbling idea, the suggestion that we may be standing on a shore, looking out at what appears to be simply water, without any way of suspecting the fish, the coral, the currents, and the deep trenches hidden beneath the surface that reveals almost nothing of what lies below it. There is one further alternative worth taking seriously: primordial black holes, formed not from the collapse of dying stars, but from the direct collapse of unusually dense regions in the primordial plasma itself, within the first fraction of a second after the Big Bang. Because they would have formed before nucleosynthesis even began, they would not be made of processed stellar material in any conventional sense, and they could, in principle, span an enormous range of masses. The idea dates back to the 1970s, proposed in part by Stephen Hawking among others, and it fell out of favor for decades as microlensing surveys placed increasingly tight constraints on how many such objects could exist. Interest revived sharply after 2015, when the LIGO Gravitational Wave Observatory detected the collision of two black holes each, around 30 times the mass of the Sun heavier than the black holes typically produced by dying stars, and exactly the kind of mass range primordial black holes might occupy. Could these be the missing dark matter? The honest answer, after several years of careful follow-up study, is probably not, at least across most of the plausible mass range. Microlensing surveys such as the Optical Gravitational Lensing Experiment, which monitors millions of stars across the Milky Way and its satellite galaxies for the brief characteristic brightening a passing compact object produces, have ruled out primordial black holes, making up more than a small fraction of the dark matter across most masses that could otherwise produce a detectable signal. Other constraints, drawn from the disruption of loosely bound binary star systems, the heating of small dwarf galaxies, and the conspicuous absence of X-ray emission from primordial black holes accreting gas in the early universe close off most of the remaining possibilities. A narrow window, around 10 to 100 times the mass of the Sun, remains technically open, but under increasing pressure from every direction. The black holes LIGO detected are genuinely interesting objects in their own right. They are probably not, however, the dark matter this story has been chasing all night. There is one more honest thread worth naming before this story closes, because it is recent enough that it belongs in any current account of dark matter's open questions. Since 2022, the James Webb Space Telescope has been observing galaxies at extraordinary distances, capturing light that left its source when the universe was only a few 100 million years old. Several of these early galaxies appear larger, brighter, and more fully formed than the standard picture of structure growing gradually out of small dark matter halos would have predicted for a universe still in its infancy. This tension sometimes summarized, with more attitude than precision, as too many, too massive, too early is genuinely unresolved. It may simply reflect that star formation in the earliest galaxies was more efficient than current models assume, a straightforward adjustment to the astrophysics of galaxy formation rather than a challenge to dark matter itself. It may point to something about the nature of dark matter's earliest clumping that current cold dark matter models do not yet capture correctly. It is too early, honestly, to know which. It belongs on the same honest list as the lithium problem and the small-scale structure puzzles, a loose thread in an otherwise remarkably successful picture, worth naming plainly rather than either dismissing or overstating. The search for the identity of dark matter has now been underway for nearly a century, and the honest summary of where that search stands is this. We know, with very high confidence, that most of the matter in the universe is not made of the same material we are. We know roughly how much of it there is. We know how it is distributed, from the scale of individual dwarf galaxies up to the entire cosmic web. We know it was cold and slow-moving in the early universe, that it collapsed into halos before ordinary matter was even free to move, and that its gravity has shaped essentially everything we can see. We know all of this, and we do not know what it is made of. Not one single particle of dark matter has ever been directly detected in any laboratory on Earth. Not one flash of light from a dark matter annihilation has been unambiguously identified anywhere in the sky. The detectors have sat in their deep caverns for decades, waiting patiently, and the signal has simply not come. This is not a failure of science. It is science doing precisely what science does, following evidence wherever it leads, even when that evidence produces a null result that forces a hard reassessment of the most elegant and well-motivated ideas available. The WIMP hypothesis was genuinely elegant. It was well motivated by independent theoretical reasoning. It has simply not shown up where the theory said it most plausibly should. The field is now in a period of open, active uncertainty, exploring lighter particles, axions, entire hidden sectors, and modifications to gravity itself, none of which has yet earned the kind of consensus the WIMP once held. One of these ideas may eventually prove correct. It is entirely possible the true answer is something no one currently working on the problem has thought of yet. And now we return to where this story began. The dark room, the quiet, the silent passage of something invisible through the walls, through the floor, through the air, through your own body. It is still happening. It has been happening for the whole of your life, and it will continue for every remaining moment of it, and you will never feel it, never see it, never touch it, and yet it makes up the majority of the material universe. For every kilogram of ordinary matter, every proton, every neutron, every electron in your body, in the room around you, in the planet beneath you, in the sun and every star visible from Earth, there are roughly 5 kilograms of this invisible substance, spread through a vast halo that surrounds the Milky Way and extends far beyond anything a telescope can directly photograph. We can map it. We can see its gravitational signature in the rotation of galaxies. in the bending of light from quasars, billions of light years away, in the pattern of hot and cold spots frozen into the oldest light in the universe. We can trace the cosmic web of filaments and voids that it built, the scaffolding into which ordinary matter eventually fell to form every star and planet that has ever existed. We can weigh it in colliding clusters and watch it separate cleanly from the hot gas left behind. We know, with real precision, where it is. We know it is passing through this room right now, through your body, billions of particles every second, leaving behind no trace whatsoever. And after nearly 100 years of looking, we still do not know what it is. 2 projects now underway may finally begin closing that gap, or at least narrowing it further than it has ever been narrowed before. The Vera Rubin Observatory, high in the mountains of Chile, and named for the astronomer whose patient, decades-long observing runs first revealed the flat rotation curves at the center of this story, began its 10-year survey of the entire visible sky in recent years, cataloging billions of galaxies and mapping weak gravitational lensing signals across a scale no previous instrument has attempted. The Euclid Space Telescope, launched by the European Space Agency in 2023, is charting the shapes and distances of more than 1 billion galaxies across a third of the entire sky, measuring the faint weak lensing distortion in each one to map how dark matter is distributed across a volume of the universe larger than any survey has covered before it, and, by watching how that distribution has changed over cosmic time, to probe the even stranger influence of dark energy pulling the whole structure apart. Neither instrument will tell us, on its own, what dark matter is made of, but each will sharpen the map considerably, and a sharper map has been, again and again across this story, the thing that eventually pointed toward the next real question. There is a long tradition, in this particular corner of science, of the answer arriving from a direction no one was watching, from a Dutch astronomer counting the vertical motions of nearby stars, from a difficult Swiss physicist applying an old theorem to a swarm of galaxies, from a woman turned away by Princeton who spent her nights measuring one faint galaxy after another until the pattern could no longer be denied. The next answer, when it comes, may arrive the same way, sideways from someone patient, looking closely at something everyone else had already decided they understood. Fritz Zwicky looked at the Coma Cluster in 1933 and saw galaxies moving too fast to be held by anything visible. Vera Rubin pointed Kentford's spectrograph at Andromeda and watched a rotation curve refuse to fall the way it was supposed to. 2 research teams, an ocean apart, independently built instruments to search the sky for a faint microwave glow neither team knew the other was looking for. Physicists have sat for decades in rooms carved out of solid rock, waiting for a signal that has not yet arrived. None of them knew, at the moment they were doing the work, exactly where it would lead. The question they were all, in their different ways, asking is still open tonight, in this room, as you listen. Good night.